What is the conventional algebraic symbol and unit of measurement for electric charge? Is it I and coulombs, I and amperes, Q and coulombs, or Q and amperes? Now, one of these will measure electric current and one will measure electric charge. The question is asking for electric charge. So in this case, the answer is going to be C. We measure electric charge in coulombs and represent it with a lowercase q. If the question was asking about electric current instead, then the answer would have been B. We measure electric current as an uppercase I in amperes, or amps for short. Question 2. What is the smallest possible unit of electric charge? Is it exactly 1 coulomb, the charge on an electron, the flow of charge per second in a circuit with infinite resistance, or the flow of charge per second in a circuit with no resistance? Let's go through our options. Exactly 1 coulomb is in fact quite a large electric charge. Most of the electric charges you work with in a laboratory will be a lot smaller than 1 coulomb. In fact, most of the electric currents that you deal with will be smaller than 1 ampere, that is 1 coulomb per second. C says the flow of charge per second in a circuit with infinite resistance. Now, we'll learn later that a circuit with infinite resistance has no current flowing, and so we get no rate of change of charge per second. So this can't be right. D states the flow of charge per second in a circuit with no resistance. Now in this case, the flow of charge per second can be extremely large, higher even than 1 coulomb per second. So D is going to be too large. The last remaining option is B, the charge on an electron. An electron is a tiny particle found in atoms with a very, very small electric charge. Now it turns out that it's impossible to have an electric charge smaller than the electron charge because all electric charges arise because of a discrepancy between the protons and the electrons in a substance. So B is the correct answer. We also represent the charge on an electron, 1.6 times 10 to the power minus 19, as E, or the elementary charge. Question 3. Define 1 coulomb. So we can do this in two different ways. We can define the coulomb in terms of electric current, or we can define coulomb in terms of how many electrons we need to get that charge. So let's write down both answers. 1 coulomb is the amount of electric charge that passes through a wire every second when there is a current of 1 ampere in the wire. We know that current equals change in charge over change in time. So rearranging the equation, we have charge, or change in charge, equals the current times the change in time. Therefore, if we have 1 ampere and we wait 1 second, a charge of 1 coulomb will pass through the wire. Now, what was the other definition we had? We define a coulomb in terms of the elementary charge. We can define a coulomb so that the charge on an electron is 1.6 times 10 to the minus 19 coulombs. And so all we need to do is take 1 divided by this number, and this will tell us how many electrons are in 1 coulomb. Question 4. An object contains 8 times 10 to the power 17 more electrons than protons. Calculate the charge on it. And here we have the fundamental charge, or the charge on an electron. Now, if the object contains 8 times 10 to the 17 more electrons than protons, that means that there are only 8 times 10 to the 17 electrons that aren't cancelled out by protons. We can ignore the rest of the electrons. They won't make a difference to our answer. So, all we need to do is figure out the total charge on these excess electrons. How do we do that? Well, we have this charge per electron and this many electrons. So we can multiply charge per electrons by electrons to cancel out electrons and leave us with charge. So an electron has a charge of this number. We multiply them together and we end up with minus 0.128 coulombs. So our answer is the total charge on the object is negative 0.128 coulombs. You might remember that with things like length and time, we often have to turn things into positive numbers. Not so for electric charge. Electric charge can be positive or negative. Question 5. A current of 1.5 amps flows through an electric circuit, powering a small light bulb. How many electrons flow through the light bulb every second? Now the key to answering this question is this 1.5 amps. This means that every second, 1.5 coulombs flow through that light bulb. So 1.5 amps equals 1.5 coulombs per second. Now the question asks how many electrons flow through the light bulb per second. So how many electrons do we need to make up 1.5 coulombs? Well, it shouldn't be too hard to work out, especially if the question gives us the elementary charge right here. If we get 9.375 times 10 to the 18 electrons, we end up with a charge of 1.5 coulombs. We can work this out using this simple division here. 1.5 coulombs divided by 1.6 times 10 to the power minus 19 coulombs per electron. And because we have a current that's positive 1.5, it simply means that the electrons will be moving in the opposite direction. So this many electrons flow through the light bulb every second. And in fact, they flow through the light bulb in an opposite direction to the electric current. So that's the end of the questions. We've learned about electric current and electric charge. Remember that electric current is the rate of electric charge per time. In the next section, we'll be looking more at how electric current works.